Okay, we want to introduce this cross product of two vectors, and here's their definition. So that's just a definition. You take A to be this determinant, or B1C2 minus B2C1. Take B to be the negative of this determinant, so the negative of A1C2, A2C1, and C to be this. And if you have that vector, they're saying, this is the cross product. And they point out that if you were to do this with the standard basis vectors I, j, and k, I cross j is k, j cross k is I, and k cross I is j, and to some extent, though, what the heck, or where's this coming from? And what I like to do is look at the idea of, okay, if I have two vectors in space, two three-dimensional vectors in space, and I would like to find a third vector that's orthogonal to those two vectors. Okay, because if I take it, if I think of two vectors in space, I could always pretend that they're both in the screen here. So one vector could start here at the I and go up this way, and another vector could start at the I and go that way. And if they aren't in the screen, just tip the screen around until that happens. Because one thing we've always said is 3 points determine a plane. You've heard that since ninth grade or something. And 1 point would be the origin, and then the other 2 points would be the heads of the two vectors. And so, yeah, I can always make a plane out of those two vectors. Now, if I have this flat screen, it seems like I should be able to find a vector that's perpendicular or orthogonal to this flat screen. And if I did, it would be orthogonal to those two vectors I started with. And so, to me, that's kind of the motivation of this cross product. Because just sort of doing this, I think, is kind of weird. And so, to look at where this came from, I did a little bit with Sage. I could have written this all out, but there's math association stuff. Okay. I went to Sage and I declared a bunch of symbolic variables here, and I made a matrix out of A1, B1, C1, A2, B2, C2. Now, what the heck am I doing there? So in the comments, I point out, well, I could make a vector X, and I did it here as a row vector, but it could be a column vector. I've got A1, B1, C1. And I've got another vector, Y, A2, B2, C2. And then I made the third vector, Z, that was ABC. Now that's a row vector, but I said make it a transpose. And that's just to kind of say that, again, I could have taken the X and Y to be column vectors or the A to be a row vector, but it just makes things cleaner here when I say A times Z. So A, I've got a 2 by 3 matrix, and then times Z, which is 3 by 1, that works. But notice if I take A times Z, that's the same thing as X here dotted with Z, X dotted with ABC, and then Y dotted with ABC, because that's how I would do that matrix multiplication. So that multiplication is just doing those two dot products. And so if we want those two dot products to be 0, now why would we want? Well, because we said we wanted a third vector here, ABC, that is orthogonal to the other two. So if I want those dot products to be 0, so x dot z to be 0 and y dot z to be 0, then that's the same thing, the way I've set this up, as solving the homogeneous problem of a times z equals 0. Because when I take a times z, the first component is going to be x dot z, and the second component is going to be y dot z, and I want them both to be 0. And so all I do is, there's A. I set up that matrix. I do its reduced row echelon form and solve for B. And so I do that. And so I've got other stuff here too. But I do that, and I get that A is equal to the negative of this thing. And B would be equal to the negative of this thing, both times the vector C, right? Because C is arbitrary. So, so I have this times whatever I do with C, and this times whatever I do with C. And because, again, C is arbitrary here. All right, so what I do is I just I take these two elements. So notice this is the 0 row second column, as in 0, 1, 2 columns. Remember, indexes start at 0, so this is row 0 column 2, and so I take row 0 column 2 of B. I take the negative of it, multiply it by my C, my arbitrary C, and that is the value of A. And then do the same thing with B, but that's row 1, column 2, and multiply by C. And then I show those two, and so there I'm saying C is arbitrary. Okay, so I show those two, and, well, it's okay if we see equal there. Notice what it did. It just said C times this, and you know, you look at this, and I can see right away that if I multiply the A1 through here, I get A2 B1 minus B2 A1, and that cancels. And you know, and I could get common denominators here, and maybe things would cancel out and so forth. And so you know, it would be nice to be able to just simplify this. Well, I tried a couple things, and I could not get it to simplify very nicely. And so I had to take another attack to kind of check these. And so what I did was I said, okay, we're going to make a substitution S here, that C is equal to A1 times B2 minus A2 times B1. Okay, and that again is what they would be saying here. Okay, so here. So, you know, I'm saying let C be the determinant that this is giving. A1 times B2 minus A2 times B1. And so I'm setting that up. And so there I just say, well, we'll let C equal that. And then I'm going to substitute that value of C into A here. You know, so I'm going to substitute that value of C into A. And I tried that, and I tried multiplying things out and so forth, and it just didn't simplify nicely. So then what I thought was, okay, I'll substitute that in for C, and then I'll just check if A minus then this value, B1C2 minus B2C1 is 0. If it is, so I'm saying if that's 0, oh, show me that it says equal. And similarly then, if I substitute in, you know, C equals this into the B, and subtract the negative of this thing, do I get 0? And if so, turn out two equal signs, you know, or equal statements. And so notice each of them spit out equal. And so if I let C arbitrarily be, so I've got a lot of choices for C. If I let C arbitrarily be this value, then A and B are these values respectively. And that's what this says. So thus A is that and B is that. And so you see, if I ask the question, how do I take these two vectors and find a third vector that's orthogonal, I have an infinite number of answers here, right? Because I can choose C to be arbitrary, but I get a particularly nice looking answer if I take C to be that determinant, and then that implies that A and B are also determinants. And so that's kind of, to me, that's where this cross product comes from, is asking that question of, given this vector x and this vector y, can I find a third vector that's orthogonal to both? And indeed I can. I can find a whole bunch of them, but in particular I can find this one nice form here where I can write A, B, and C as these determinants. Okay, and so that is to me the motivation for coming up with this cross product of two vectors. There are other motivations as well, but I kind of like this one of just finding that vector that is orthogonal to the other two. All right, so we'll call that one done.